I'm going to assume that you already know what Pythagoras' theorem is, that the formula for it is a squared plus b squared equals c squared, but that what you're really here for is to know why the theorem works. I'm going to split this video up into two parts. The first is a simplified explanation of the method that I'm going to use to prove the theorem, and in the second part I'll be showing the step-by-step process for proving the theorem is true. If you just want to see the proof, then just skip ahead to this time that I'm leaving on screen, but you can always come back to the first part if you skipped ahead. So here's a brief explanation of the method that we're going to use to prove the theorem. As you can see, we have a quadrilateral, the edges are of equal length and adjacent edges are perpendicular, so this is a square. The area of this quadrilateral must be x squared. But let's say I decided to cut the square across the diagonals. What would that look like? Well, we would still have the square with the same area, but one that has been bisected across each diagonal. The result is 4 triangles where the base of each triangle is x, which is just the length of the side of the square, which means that we can describe the area in terms of these 4 triangles. Here's one of the triangles with the base x, but what if the smaller shapes didn't make up the entire area of the square? For example, let's say I cut off the top of the triangle. This creates a trapezium, which has a smaller area than the original triangle. So if I fit 4 of these together, they won't cover the same area that the 4 triangles covered. But can we use this shape to describe the whole area? I'm going to give the length of the top edge a value of u, and let's call this shape tz for trapezium. If I replace these 4 triangles with 4 of these trapeziums, here's what we get. The 4 trapeziums cover most of the x squared area, but there's a small square area in the middle that's not covered. The edges of that square are just the length of the top of one trapezium, and that length is u, so the uncovered area must be u squared. So we can express the area x squared as 4 of these trapeziums with the missing area in the middle, which is u squared. So x squared is 4tz, which is 4 times the trapeziums, plus u squared, which is the gap in the middle. And so we've been able to describe the area of a square using a shape that's not a square itself. This is the method that we're going to use to prove Pythagoras' theorem. So let's begin the proof. I just quickly want to point out 2 things. The hypotenuse, the longest edge of the triangle, is opposite the right angle. This must mean that the sum of the angles adjacent to the hypotenuse is 90 degrees. Whenever you see a compound angle containing both blue and yellow, the angle must be a 90-degree angle. That and the fact that the hypotenuse is opposite the original right angle is something that will come in handy later on. I've made things a bit smaller to give us room for our calculations. And there's one more thing I forgot to point out, and that is, as you know, the area of a triangle is given by half base times height. The base of this triangle is b and the height is a. I'm going to call it half a times b. It doesn't matter which way around you have the edges in the equation. Now, just as in the demo, I'm going to use 4 of these triangles to construct a square area. I'm going to begin by laying a triangle on its hypotenuse. Note that the small edge a is on the right hand side. Now I'm going to position a triangle to the right. The edges a and b are adjacent, and notice that they begin at the same point. I'm going to do exactly the same thing with the next triangle, that is, place it so the edges a and b are adjacent and begin at the same point. And I'm going to add one more triangle with exactly the same effect. The edges a and b are adjacent and they begin at the same point. And that results in the last and first triangle having the same property. The edges a and b are adjacent and begin at the same point. The shape is now complete and it clearly is a quadrilateral. In order to be a square, the edges must be perpendicular, which is the same as saying that the internal angles must be 90 degrees. And all of the edges have to be of equal length. You can see that the angles in this shape are composite angles, and each composite angle is made up of 2 colors, blue and yellow. We established earlier that the sum of blue and yellow angles is 90 degrees. All of the internal angles are therefore 90 degrees. We just need all of the edges to be of equal length. We'll notice that each edge of the quadrilateral is just the edge of an individual triangle that's opposite the right angle in the triangle. And earlier on, we showed that that must be the hypotenuse. So each edge of this quadrilateral is the length of the hypotenuse c, so this must be a square. And so the area of this quadrilateral must be c squared. And now, just as in the earlier demonstration, we're going to express the entire area of c squared in terms of the 4 triangles. Most of the squared area is made up by the 4 triangles, and then there's a smaller section in the middle. So c squared must be the sum of 4 triangle areas plus this middle section. The area of one triangle is half AB. We're using 4 of them. 4 times half is 2, so the area covered by all of the triangles must be 2AB. Now we just need to figure out the area of the small section in the middle. I'm going to make the B edges of all the triangles a different color, purple, so that they stand out. And notice that the edges of the inner section are made up of parts of the length of the B edges. The length of the white edge, which is adjacent to the purple edge, is A, so the part of the edge B, which isn't adjacent to the edge A, must have the length B minus A. Because if this is B minus A, and then you add the length A to it, B minus A plus A equals the entire length B. This applies to all of the pairs of adjacent triangles, so we have a quadrilateral where the length of each side equals B minus A. But this shape has one more property. Adjacent to each corner angle is a right angle. The external angle is 90 degrees. The internal angle and external angle are on a straight line, so the internal angle must be 90 degrees, and this applies for all 4 corners of the shape. So this is actually a square with side lengths B minus A. The area of the internal section then is B minus A squared, which means that the entire area can be expressed as 2AB plus B minus A squared using a right angled triangle, and that must be the same area as C squared. We have just one more step, and that is to expand the brackets to see what result we get. First of all, we have B times B, which equals B squared. Then we get B multiplied by minus A, which equals minus AB. Then we get another minus A multiplied by B, which gives us another minus AB. And finally, we have minus A multiplied by minus A. 2 negative numbers multiplied gives a positive number, so that gives us A squared. We can simplify this further because we have 2 minus ABs, so that's minus 2AB. And so we get B squared minus 2AB plus A squared. And so we can replace B minus A squared with this result, giving us 2AB plus B squared minus 2AB plus A squared. 2AB and minus 2AB cancel, which means that the area is B squared plus A squared, but that is the same as C squared. And that means that A squared plus B squared equals C squared, which is exactly what we were setting out to prove. That in a triangle with lengths A, B and C, where the longest length, the hypotenuse, is C, A squared plus B squared equals C squared, and so Pythagoras' theorem is true. That's it for now. Thanks for watching.